just finished up talking about continental drift and Alfred Wegener and his sad story. But the resurrection of his idea begins with seafloor spreading, and that's what we're talking about today. This idea that the seafloor is constantly moving, it didn't make sense to anyone in Alfred Wegener's time. They didn't realize that that's really what was happening. It wasn't until much later, after World War II, when we really began understanding that the ocean floor, it's being made little by little every day, and it wasn't made all at one time a long time ago. The beginning of seafloor spreading actually starts in the 1800s, when people started to map the ocean floor. And a long time ago, they would sail a sailboat around and they would just throw in a weight on a rope. And they would just measure how much rope it took to have that weight hit the bottom of the ocean. They'd write down that number, they'd pull the weight and the rope back up, and they'd sail a little bit further along, and they'd do this again and again, mapping the depth of the ocean floor. Fast forward to around World War II, and new technology became available. Things like sonar, sound navigation, and ranging. The ranging means they can take a depth of the ocean floor. And they used this in World War II in the Pacific. When we were going from island to island, we had to know how close to that island we could get our ships. So they used sonar to figure out how deep the water was. Luckily for all of science, one of the captains, someone who ran a ship that had sonar, was actually a geology professor. And so he just kept his sonar on his entire trip through the Pacific Ocean. And he started to map the bottom of the ocean floor like it had never been mapped before. And both using a line and a weight and sonar and newer techniques later on, we discovered that the ocean floor isn't anything like what people assumed it was. A long time ago, people just assumed when you walk into the ocean, it gets deeper. And it's probably deepest in the middle, and then it gets more shallow as you go to the next continent. That's kind of what makes sense. But that's not what the ocean floor is like. Some of the features they found on the ocean floor are things like deep ocean trenches, extremely deep, thin lines on the ocean floor. And when I say extremely deep, I mean like close to 7 miles below the surface. They also found mountain ranges. Like in the middle of the Atlantic Ocean, there's something we called a mid-ocean ridge. So right in the middle of the Atlantic Ocean, where people would assume it was the deepest, it's actually a mile taller. The sea floor is a mile higher than the surrounding ocean floor. And we found in the middle of that mountain range something called a rift valley. And this rift valley is where volcanic eruptions take place, that we'll talk about in just a minute. And so some of these discoveries led to further curiosity about the ocean floor. And so there was more and more research done on the ocean floor after World War II. And some of that research just led to basic things like composition. We really found out that the majority, almost all of the ocean floor is made out of basalt and gabbro. And we also realized that there's a pattern with the amount of sediment on the ocean floor. It's not equally distributed. It's not one even blanket of sediment across the entire ocean floor. No, it's not at all. The sediment is actually much thicker closer to the continents, and in the middle of the ocean, like the Atlantic Ocean, there's almost no sediment present whatsoever. Even further research on the ocean floor allowed scientists to take core samples. So physical samples from the ocean floor that they could use radioactive dating for, and then we could find out the age of the ocean floor. And when we did that, they saw that the ocean floor is not all the same age. It is actually much younger, right in the middle of the Atlantic Ocean, right in the middle of our ocean basins. And this led scientists to the idea of seafloor spreading, where the ocean floor is made at one of these mid-ocean ridges, and then it moves towards, you could say, the continents, or moves away from that mid-ocean ridge, and then the ages get older and older. And there's really 3 distinct steps in seafloor spreading. One is the eruptions. And these aren't volcanic eruptions like you might think in your head, like boom goes the dynamite and there's massive lava flows. No. These are very small micro eruptions, which is really more magma filling small slivers and cracks in the ocean floor. But it's doing that consistently all the time, every single day. And that force of those eruptions causes a movement. If we're adding a bunch of material in the middle, it's going to force the ocean crust to move apart. But if the ocean was constantly growing, and nothing else was taking place, our entire planet would get larger if the ocean crust was growing. And that's not happening. So at the same rate the ocean floor is growing, it's also being recycled or destroyed in places that we call subduction zones. And this whole process, eruptions, movement, and subduction, is kind of how we summarize and talk about seafloor spreading. Just like continental drift, seafloor spreading has several key pieces of evidence as well. And one of those are just these magnetic strips on the ocean floor. When they took those core samples from the ocean floor, they ran them through really expensive and large magnets, okay? So they could tell the polarity or the direction the minerals in those rocks pointed. And what I'm talking about are minerals like magnetite. We know magnetite is magnetic. And when magnetite first crystallizes in magma, it's almost like a compass needle. It's gonna be a magnetic mineral floating in a liquid. And since it's floating in a liquid, it can align itself like a compass needle with the magnetic north and south pole of the day that magma cools. And since every so often Earth's magnetic field flips, meaning that it reverses, meaning that your compass, instead of pointing towards the North Pole, your compass would point towards the South Pole. When those reversals occur, it's preserved on the ocean floor because those magnetic minerals, they shift in a very short period of time from pointing towards the North Pole to reversing and pointing towards the South Pole. And that stuff we can see in our core sample. We call this paleomagnetism. And it's really just the study of ancient magnetism. So if the entire ocean floor was all made at the same time, it would all show the same polarity. But it doesn't. It shows these constant reversals. And that's just evidence that our ocean floor was made little by little and not all at the same time. It's evidence for seafloor spreading. Other evidence would be earthquake patterns. And this is really evidence for subduction. This is how we know subduction occurs. Because earthquakes occur when stress is put on a rock and that rock breaks, releasing energy. And we have recorded earthquakes deep into the mantle. And if you remember, the mantle is kind of like that Laffy Taffy, it's plastic flow. It's not solid enough to build up energy to have an earthquake. So how could we possibly get earthquakes that deep into the mantle? The answer is subduction. We take the rigid crust and it is subducted and forced into the mantle where there's pressure on that subducting chunk of crust, and that pressure eventually leads to earthquakes. And when we pair that depth with an earthquake with the distance from a subduction zone, we can really kind of track and see the degree at which an ocean plate subducts in the mantle. So when our earthquakes are shallow, they're much closer to where the subduction begins, the ocean trench. And when the earthquakes are very deep, they're very far away from the subduction zone. And that shows us the angle at which these plates are subducting. The very last piece of evidence we'll talk about, and maybe one of the strongest pieces of evidence, is just simply the age. Like I said, we took core samples from all over the ocean floor, and it is not the same age. And that is a direct piece of evidence that the ocean floor was made little by little through seafloor spreading, and not all at the same time. And that also explains why the sediment layer is so much different on the ocean floor. Because this brand new ocean floor in the middle of the ocean doesn't have much time to collect sediment at all. But as you go away from that new ocean floor towards the continents, the sediment becomes much thicker because that ocean floor has been there for millions of years collecting ocean sediment. And that's the idea of seafloor spreading. And this idea of seafloor spreading started to produce those mechanisms for continental drift. So once we knew that the ocean floor was spreading apart, that kind of gave a mechanism for continental drift taking place, but we're still missing one part of this mechanism, and it's really just what causes seafloor spreading. And that's what we're going to talk about next time. So make sure you're filling in your notes. If you have questions, make sure to ask. Thanks.